All right, this is section 7.2, which is on predicting properties through excuse me, attractive forces. All right, let's do a little review of change of state. Right? You will remember we have solids, liquids, and gases. We talked in chapter 5 about how liquids have more energy and more molecular motion than solids. Gases have more molecular motion than liquids. Well, how does that translate to them changing phases? It comes down to this concept called intermolecular forces, which we will revisit shortly in this video. Essentially, to go from a solid to a liquid, we have to overcome the intermolecular forces, the forces that are holding our molecules, or really more broadly our particles together. How do we do that? Typically we do it by increasing the temperature. Go from a liquid to a gas, we have to overcome those intermolecular forces even more still, right? So, that's what we have going on with this. Right. Now, let's talk about this concept called vapor pressure. So, if we picture a sealed container that has some amount of liquid in it, at any given time, for a given temperature, some of these liquid particles are going to have enough energy to come out into the gas phase. Now, if this is a sealed container, we stick a gauge on here and measure the pressure. We're going to be able to measure a certain pressure in here. Right? Now, what is that pressure dependent on? First of all, it's very, very highly dependent on the substance. But secondly, it's dependent on the temperature. All right? Now, if we were to look at water, just for example, we would find that at 100 degrees Celsius, the VP of water is 760 millimeters of mercury, or 1 atm, which, if you will remember, is normal atmospheric pressure. Now, if you also remember the significance of 100 degrees Celsius, that's the boiling point of water. And this actually leads us to a definition of boiling point. Boiling point is where vapor pressure is equal to atmospheric pressure, or more properly, it's where vapor pressure excuse me, is equal to ambient pressure. Okay. Now, let's talk a little bit more about what these attractive forces are that hold these together. There are 3 of these that I'm going to talk about, and I always teach them actually in a different order than your book addresses them, just because I think it makes a little bit more sense to talk about them this way. All right, if you will think back to chapter 3, when we talked about dipoles, let's think of, just for example, a carbon-oxygen bond. Let's put it as part of this molecule. Now, these carbon-carbon bonds are nonpolar, carbon-hydrogen bonds are nonpolar. We consider those to be nonpolar. But if you will remember, oxygen is very electronegative. Carbon is more electropositive than oxygen. Electropositivity, of course, is the opposite of electronegativity. And so we have this partial negative charge on this oxygen. We have this partial positive charge on the carbon. That gives us the dipole that looks like this. Right? Now, if we think of this, though, let's say that we have another of these molecules. Or it could be another molecule. It could be a different molecule with a dipole of some sort or another. But let's just say it's another one of these molecules. We align it over here like this. Right? And there's going to be our negative charge. There's going to be our positive charge. There's our dipole arrow. Now, if you look, we have a negative charge here next to a positive charge. Positive charge next to a negative charge. Right? This type of, and opposite charges attract. So this type of interaction leads us to what's called dipole forces. Okay? Now, we can also look at what I sort of consider to be a special case of dipole forces, even though it's such a strong intermolecular force that we give it its own name and classify it separately. This is something called hydrogen bonding. Now, even though we call this bonding refers to it being an attractive force, not to it being a chemical bond, right? Hydrogen bonding is an attractive force. Now, how does hydrogen bonding arise? Hydrogen bonding exists when we have a hydrogen chemically bonded to O or N. Now, if you've taken a chemistry class before and you're watching this and you're thinking, but what about fluorine? Yes, but there's only one compound where that's the case, so we're just going to kind of ignore that. Really, we care about O and N. But hydrogen chemically bonded to O or N that is attracted to an unshared pair of electrons. Right, now, our single most important compound that we have that can hydrogen bond is this one here. Kind of important, right? Water. All right, we look here, we have a hydrogen bonded to an oxygen. Now, let's stick another water molecule over here. Okay, this hydrogen is attracted to these unshared electrons. This hydrogen attracted to these unshared electrons. We could go on and on and on with this. Now, this doesn't have to be two molecules of the same substance. Just for example, we could have this molecule, hydrogen bonding with, let's say, ammonia. All right, that's a hydrogen bonded to an oxygen. That's going to be attracted to these unshared electrons on this nitrogen. This is a hydrogen bonded to a nitrogen. Sorry, that should be an H right there. Going to be attracted to this hydrogen bonded to nitrogen, attracted to these unshared electrons. Now, none of these other hydrogens can participate in hydrogen bonding because they're not chemically bonded to an O or an N. Right. That's hydrogen bonding. Now, our third type of intermolecular force really, to me, is the most abstract one. This is called the dispersion force, or your book calls it the London force, named after the guy who discovered it. Or we could call it London dispersion forces. Right, London dispersion forces. Now, the way these come about, let's look at a completely nonpolar bond, like say a carbon-carbon bond. We will remember a covalent bond consists of two electrons shared between two different atoms. Now, we model them on average as spending equal time at both of these, which is true for a nonpolar bond. But we could have this situation where, just for an instant, maybe both of these are over here. Now, if both of these electrons are next to this carbon, that's going to give us a little bit of we're going to give us a partial negative charge on this carbon, and give us partial positive over here. All right, now, let's say, and this just happens for an instant, but at any given time, we're probably going to have a couple that are doing this, or probably actually quite a few, depending on the size of the molecule. All right? So let's say we have one here, all right? Partial negative, partial positive. They're going to be attracted to each other, all right? Now, this just happens for an instant, and it falls apart. But this is going on enough because, remember, we're dealing with huge samples with huge numbers of molecules. So it's going to be happening often enough that this can hold molecules together. All right, if we rank the relative strength of our attractive forces, dispersion forces we usually consider to be the weakest. Then dipole-dipole. Then hydrogen bonding. Right, dispersion, dipole-dipole, hydrogen bonding. Now, something else that's important to remember with this is that if we have hydrogen bonding present, there's also dipole-dipole, there's also dispersion forces. We have dipole-dipole forces present, we also have dispersion forces, right? So, if you're asked to identify what's the dominant intermolecular force between two molecules of the same compound, you will look for which of these could be present. You'll identify the strongest one. If you're asked what intermolecular forces are present, you look for the strongest one, then you list all the ones that are less strong. All right, that covers 7.2, which is on intermolecular forces.